All right, let's get to revise now as far as binary systems or just number systems in general, number systems are concerned, right? So what I'll be doing with these revision sessions, I'll be just cropping questions that have to do with the topic that we'll be revising in that day. So for the meantime, let's, looking at this, we are supposed to be revising on, we're supposed to be revising on binary on number systems. So if you check a look at this, you will see now which year I have taken this paper from. So you are now at the liberty to go ahead and probably just do the part on checking the mark scheme by yourself if you want, or even just getting on the paper and revising and ticking by yourself that probably this paper we would have done it. Yeah. So to start with, our first concept that we need to revise now is pertaining, the first question that we have is state the difference between kibibyte and megabyte. State one difference between kibibyte and megabyte. So what we have here is that when we talk about kibibyte, we're talking about binary prefix. Yeah, binary prefix for this one. But when we talk about megabyte, megabyte is actually binary prefix. So that can actually stand to be actually a difference that megabyte is a binary prefix because it goes with 10 to the power of something. Then kibibyte, it goes with 2 to the power of something bytes. I hope that makes sense. And if you want, you can actually still mention that a megabyte is bigger than a kibibyte. That's also a valid reason, a valid difference. But rather, my best difference now, my best response for this now is to indicate the number of bytes that we need to form a kibibyte. Right? The number of bytes that I needed to form a kibibyte are going to be we can just say a kibibyte. Kibibyte needs about 1024 or the 2 to the power of 10 to the power of 10 of bytes. You see that? Then when we talk about the part now on megabyte now, it's in binary prefix, yeah? Megabyte. That's going to be coming through now to be 10 to the power of 6 or 1 million, right? 1 million bytes. So coming through to tell us that a megabyte is bigger than a kibibyte is okay, but rather I would appreciate or I would love it if you actually give us the difference in this sense, that a kibibyte is bigger. A kibibyte needs only 2 to the power of 10, but a megabyte needs a 10 to the power of 6 bytes. You gotta tell us that we're talking about bytes here. You get the point? So that we can actually see by ourselves that which one is bigger. That's basically what we have as far as number one is concerned. All right. Number two, convert the binary number, the binary value into a 12-bit 2's complement. It's 12-bit 2's complement, right? So we have negative 196. We are asked to put it now into 12-bit 2's complement. Negative 196. There are two ways of doing this. You can first express 196 into a value that's going to be coming through to be, you can first express 196 on its own into binary, then you add a 1, you flip the ones, then you add a 1. That's one way of doing it. Or just going straight up to put a number line in its 2's complement, then you give us a value, which is my personal favorite. So putting that number line, I'm going to be having something like what? Matter of fact, let's just do both methods. One way of doing it is the part that you convert 196 into a 12-bit binary number that is not signed, not 2's complement, but just a binary number. So if we're talking about 196, you need 1, 2, 4, 8, 16, 32, you need 64, you need 128, right? I can just put it probably in this state so that I need 1 here. I need, if I take another 1 here, I'm already on 196. Nope, I'm on what? On 192. This is 192. 192 adding a 4. now 196. So that is exactly what I need. So this is now in its 8-bit state. So, but I'm asked to put it in 12 bits, so I need to add other zeros here. 1, 2, 3, 4. So I now have a 12-bit presentation of positive 196. Right? The next thing that I need to do now is to flip all these now to put it in 1's complement. So putting this in 1's complement, every 1 flips to be a 0, every 0 flips to be a 1. So now I have a 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, 1, 1. That's basically what I need to do. Then the last thing that I now need to do now is to add a 1. Right? I add a 1 to the least significant bit to put it now into its 2's complement. So what I now have now is my solution is going to be coming through like this. So I will take now 1 plus 1, that's going to be 0, carry 1. 1 plus 1, that's going to be 0, carry 1. 0 plus 1, that's going to be 1. Everything else comes as is. 1, 1, 1, 0, 0, 1, 1, 1, 1. This now becomes my answer now in 12-bit. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This becomes now my answer. So check this out. To convert your number into its 2's complement, you first put the number, you take first the positive state of the number. You convert that into binary, right? Converting a number into binary is pretty simple. You just need to put a number line that goes through with with a binary prefix. That's 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 5, 6, and 7. So what you're going to be doing next now is you are now looking for numbers or digits that are up here that we need for us to get 196, I mean to say. You get the point? So you can start by saying what? If I need 196, what is the largest number that I have here that is close to 196? Here we have 198. 198, we put a 1 on that. What are we left with? We can add a 64, and adding a 64 and a 4, we can get to our number, which is 196. So you are now in the basic binary. If you flip every digit here, if it's a 0, you get a 1. If it's a 0, you get a 1. If you 1, you get a 0. That's now putting a number into its 1's complement. If you then add a 1 now to the flipped binary or to the flipped value, then you now get your number now in its 2's complement. Right? So the solution that was expected here was 1, 1, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0. This is my number in 12 bits 2's complement. That's basically what you're supposed to do. I hope that is understandable. When you're not talking now about the second item, convert into BCD. This is the simplest form that you can ever get. Convert this into a BCD, binary coded decimal. You just need to group your BC. Convert the BCD. I mean to say sorry for that. Convert the BCD into denary. You just need to have this arranged in pairs of 4s. So you'll be like in groups of 4s. 1, 2, 3, 4. 1, 2, 3, 4. Then you just convert these into what? You just convert this into denary. Yeah? So you're coming through to say this is a 0, a 1, or a 2. Sorry. This is going to be a 1, a 2, a 4, and an 8. Again, 1, 2, 4, 8. Again, 1, 2, 4, 8. So here I gotta add, I have only 8. Here I have to add 4 plus 2. Here I have to add 4 plus 1. So my solution, this will give me a 4, and 8, I mean to say, this will give me a 6, this will give me a 5. So at the very end of the day, converting this number will give me an 8, 6, 5. That's the general value that is represented by this BCD. Pretty simple. So maybe just a touch base on BCD. BCD is a number system now that allows any denary number from 0 through 9, right? Only from 0 to 9 to be converted into their BCD state. So we're converting any binary number, we're converting it into its binary, into its 4-bit binary state. So if I have a number, even a number like, let's say I have 1, 2, and 3 as my binary number, then converting this to BCD, 1 has to be in 4-bit binary, like 0, 0, 0, 1. 2 has to be in 4-bit binary, like 0, 0, 1, 0. 3 has to be in 4-bit binary, like 0, 0, 1, 1. This is the representation of this number in its BCD state. So we're saying you just take each digit and you convert it. You just take each digit and you convert it into a 4-bit binary value. That's how you just convert numbers into BCD. That's pretty much what we have as far as this is concerned. I hope that's making sense. So I'll clear the screen and I'll move on now to the next part. Right. The second part now, the second part is asking us now, convert the unsigned binary integer to its binary state. So this number is now in binary, but we want to convert it into denary. What I just gotta do here is to make sure that I put the corresponding denary values. This is a 1, a 2, a 4, 8, 16, 32, 64, 128, 256, and so on and so on. I don't need to be putting these white because I don't have their corresponding they are all zeros, so there's no need of actually putting that into check. So what I have here, I have a 256, I have a 128, oh come on, I have a 128, I have a 64, I have a 16, and I have a 4, and I also have a 2. Those are the values that I have. Let's check that one more time. 1, 2, 4, 8, 16, 32, 64, 128, 256. So you're now adding these numbers all together. 6 plus 6, that's going to be a 14, 18. Okay, let's just have it like this. This and this, that's a 10, 20, 30. Yeah, the 0 carry 3. 7 plus 7, that's 14, plus 3, that's going to be giving me a 7 plus 3, that's going to be giving me it's 14 plus 3, right? 7, 9, 14 plus 3, that's going to be a 17. Carry 1 there now. 2, 3, that's now a 4. So my number here is going to be coming through as 470 in denary. Yeah, pretty much simple. You just have to be, you just put the denary corresponding values for this number. The next thing that you're going to do is now to multiply 1 times this. If I had the corresponding this 256, 5, it should be 512. Is it 512? Yes, 512. 512, 10, 24, 10, 24, 252, 20, 48. So if I multiply by 0 now, then these are going to be still giving me a 0. 1 times 256, that's 256. 1 times 128, that's 128. 1 times 64, that's 64. 0 times 32, that's 0. 1 times 16, that's 16. 1 times 4, that's 4. 1 times 2, that's 2. You add those numbers together, then you get your number now in its denary state. That's going to be coming through as in base 10. It's 470 base 10 like that. Right? The next question that we have now is identify one practical application of BCD and justify why BCD is used in this application. Yeah. So we can use BCD in quite a number of gadgets, but rather we can talk about BCD being used in electronic displays, right? Electronic displays. We're talking about the part now when we're talking about digital watches, when we're talking about the part of digital boards, we can talk about calculators, right? We can even talk about digital clocks, as I mentioned before. Digital clocks. When we talk about BCD being used in this thing, we're talking about representation like time. Time is going to present, let's say it's 8 o'clock in the morning, it's going to be coming through like this. Well, it's going to be coming through like this, or we don't have this middle part like this. This is how my 0 is going to be structured like. Right? Like this. This is how they're going to be showing us that it's 8 o'clock in the morning. So that's how you can easily see that this is BCD. So whenever you're going to be seeing a display that's going to be coming through like this, just know that that's your BCD. That's a BCD logic that is being used on that. I hope that makes sense. Why do people even love to use BCD so much? They love to use BCD because BCD allows us a simple conversion, right? Because there is simple the conversion that is between ordinary and BCD is pretty much easier, right? That's what I will be expecting to see now is a solution, as a reason or a justification why people go ahead to use BCD in most of their technologies. Yeah. All right, that's what we have as far as this is concerned. I just took some time to go ahead and explain how you convert numbers into different number systems, and again BCD state, and again why we need to use BCD as far as this is concerned. I hope that made sense. So what I will do is I want you to pause the video now to go ahead and maybe check on how you could solve these now. We have converting this into hexadecimal, which is pretty simple, into BCD, again, converting this into 8-bit, into their 2's complement 8-bit. You make sure that you master this. You go ahead and again and do this. Convert the following binary integers into their 8-bit, into an 8-bit binary, pretty simple. Convert this into its BCD, pretty simple. 2's complement, that's pretty simple now. Convert this one now into its binary state, pretty simple. I'm pretty sure that you can be able to solve this. And you can now go ahead and check with the mark scheme if you got it correct. But rather, I can even go ahead and actually solve this, but with little and minimum explanations with it, because I spoke a lot in the first chapter. So converting this now from binary to hexadecimal is pretty simple. I have to convert this into sets of 4. 1, 2, 3, 4. So I check this now. This is 1, 2, 4, and 8. 1, 2, 4, and 8. So here I have to add 8 plus 2 plus 1, which then gives me an 11, and an 11 is represented by what? By B, right? Then here I just have an 8, so I'm going to be taking that as 8 like that. So my solution is B8 base 16. That's what's up. Then here, convert the following into BCD. Just split that. I need a 4-bit representation for. I need a 4-bit binary representation for 9. 9 is 1, 0, 0, 1. For 7, it's 0, 1, 1, 1. That becomes my solution. Right? Then the next thing, I need to convert these null into their 2's complement. But this time around now, I'm going ahead to have these. To solve this by using the second method, you can just go ahead and put the binary representations for this. This is 1, 2, 4, 8, 16, 32, 64. Oh, this is 32, 64, and 128. But because it's 2's complement, the most significant bit here has to be negative. You get it? So now, to get a 148, I don't need no negative number to get a positive 148, but I need this. So if I have 64 plus 32 is going to be giving me something like 96. 96 plus 64 plus 16, right? We have 96. We are adding null a what? A 16. We get a 2 there, carry 1. We have null a. That's a 10, and now an 11. That's going to be 112. I'm now left with 2. I need a 2 here to get to 114. Plus 2, I get to 114. So all these now become zeros. That's pretty much what I have to do here for me to get the value of 148, right? Then let's just clear the screen and make sure that and see how we can solve negative 93. You can do the very same thing like how we did before. You need to have your number line or the corresponding values 1, 2, that's a 4 now, and 8, 16, 32, 64, and a negative 128. Because I'm dealing with a negative number, I definitely need a negative 128. If I add 64, I'm now getting to negative 64. I don't need this. If I add 32 now, if I say negative, if I go ahead and say negative 32, sorry, if I go ahead and say negative 128, what am I saying? If I say negative 128 plus 32 now, right? Negative 138, you can actually give me the answer. You can calculate that by yourself. Negative 198, negative 128, I mean to say, sorry. We want you to we want you to go ahead and add 32, right? I hope your answer is as good as mine, which is a negative 96. So if I take this now, I'm now on negative 96. So I now need to add a 3 to this so that I can get to negative this. So a 3, I can get a 3 by taking these 2. So these now become zeros. So my solution pretty much comes like that. So if I say, you can even try it by yourself, negative 128, right, plus 32 plus 2 plus 1. You get your answer as negative 93. That's pretty much how you can do it, right? I don't know if there is any question. If there are no questions, if there are any questions, you can still touch base with me, but rather I'm going to be going ahead and actually scroll this to solve the last part, which you have 5. I'm asked to convert this into 8-bit denary. This and this, pretty much these are pretty much, all these, the ones that are remaining here, you can do them by your own, even using the examples that we did on the top there. But because we are doing a revision, I might as well do them for you. We have 1, 2, 4, 8, 16, 32, 64, and 128, because this is not in 2's complement, just an ordinary number. So I need a 32. If I take a 16, I'm now on 48. 48 plus 8, that's now 56. I don't need that, but I need this definitely to get to 52. 52 plus 2, that's 54, plus 1, that's going to be 55. So all these are going to become 3 zeros. This into binary coded decimal, we want to put this now into, this is the binary coded decimal, we want to put it into denary. We just need an 8 there, an 8, and this is a 3. That's all that we need to do. This negative 102, that's 1, 2, 4, 8, 16, 32, 64, and negative 128. It's a negative number, so I gotta take this. If I take this, it's negative 64, I don't need it. If I take this, it's negative 96, I don't need it. If I take this now, that's negative 112, I need this. Negative 112, I only need to add a 10 for me to get to 102. So a 10, I can get a 10 by saying 8 plus 2. So all these now are going to become 3 zeros. So you can test it by yourself. Negative 128 plus 16 plus 8 plus 2, you get a negative 102. Please touch base with me if there is any problem in actually dealing with these type of examples. I just shown you 2 examples on how you can convert a number into its 2's complement. Then that's going to be my solution. So I'll clear this before I go back to actually solve the last part, which is asking me to put this into denary. One way of putting this into denary that I love is maybe just multiplying this. That's 4 multiplied by 16. We add that with E, that's a 14 now, multiplied by 16. Oh, this will be to the power of 0, this to the power of 1. So this is just a 14 multiplied by 1, which gives me a 14 plus 16 times 4, that's going to be giving me something like 64. So adding these together, now you get something like what? Like 78. 78 base 10. This is going to be my solution at the very end of the day. That's pretty much what we have as far as the revision on number systems is concerned. Touch base with me if you are still finding something a little bit challenging. Otherwise, let's meet in the next video.